Okay guys, welcome. This is Math 2. We're on day 2 of piece-wise functions. We didn't quite finish our notes yesterday, so we just want to talk about what the graph of absolute value of x looks like as a piecewise function. So first thing I did was I just went ahead and graphed what we already know is the absolute value of x, and I realized that all my action is happening right here at x equals 0. Okay, so I divided the graph up into two pieces. I said it's the red part and the green part. Now, as a review from last year, I can write y equals mx plus b because I clearly have two different lines. This is linear, and so is this. So I remind myself of what those things mean. Now let's look at the green part. Okay, the slope of the green part is up 1 over 1, up 1 over 1, so my slope is a 1. The y-intercept is right here at 0, so my y-intercept 0, which gives me the equation y equals x. So the green equation right here is y equals x. I'm going to do the same process for the red one. Here I recognize that I'm actually going down 1 over 1, so that's a negative 1.
You going to the meeting? I'm just checking.
Alright, so what I did here, I went ahead and finished, I wrote my equation for the red graph and the green graph, and now I had to talk about when do I use the green graph. Well, the green graph happens anytime I'm above 0. So all of these numbers are above 0, and the red graph happens anytime I'm below 0. So I almost have a piecewise function written out. I'll go ahead and write that out. But I want you to notice there's actually one piece missing. I've never taken care of 0. 0 is not on either one of these, so there's a couple ways for me to take care of it. One, oops, whoa. Sorry about that. One way is to take care of it is to just absolutely define it at 0. Okay, and this is the book definition. This is what the book would say that it is. Now, I would argue that you don't necessarily need 3 pieces of a piecewise function. If you wanted to, you could get rid of that, and you could just simply put either one of these as equal to 0. So perhaps I make the top one greater than or equal to 0, and leave this one as, make that one a closed circle and this one an open circle. Or, of course, I could do it the other way, and I can make the bottom one. It really doesn't matter, it's all the same thing. Take a minute to look over that and anything you need to. Alright guys, because of the absolute value, we went ahead and tried to graph 2 of these and just on a piece of graph paper off to the side. There are different ways of doing it, but since we've already studied transformations, honestly, it's the easiest way for basic ones. So if I were you, I would look at these and recognize that both of these are absolute value graphs, so the parent graphs look like this. Okay, I would use what we know about transformations. Now this transformation is on adding 2 on the inside of the function, which means this function is being translated to the left 2. So I take every single one of those points, I move them to the left 2, and there's my function. Now over here, I'm multiplying by 2 on the outside, and we know that is a vertical stretch. So that means all of these points are being stretched upwards. And because it's 2, we know it's being stretched upwards by a factor of 2. So I'm going to take these two, instead of going up 1, I'm going to do 2 times that. And they're at there, and they're up at 2. Instead of these guys being up 2, they're going to now be up 4. Instead of these guys being up 3, they're going to be up 6. And you have your line vertically stretched.
Jesse Connor, come to the office,
Alright,
please.
on the back of your
Connor,
notes,
please come to the
we were
office.
looking at a different kind of function. Okay, first thing we decided, just taking our time, was we decided that the money that we're going to be charged is going to depend on the number of hours that we rent the equipment. So we found out that the money was dependent, which is our y variable, time is independent, it's our x. We're going to make a little chart over here and just come up with some sample charges. Okay. I think we all understand that if I rent it for 2 hours, I'm charged $2. If I rent it for 4 hours, I'm charged 4 hours. And if I rent it for 6, I'm charged 6. But the question is, how much are you charged for 1? And that's a little bit harder to think of. Remember, you're being charged $2 for every 2 hours or any fraction thereof. So even though you only had this for 1 hour, they're still going to charge you $2. Even if you only rent it for half an hour, they're still going to charge you $2. Even if you only rent it for 10 minutes, which is a sixth of the hour, they're still going to charge you $2. So you can see things look a little different. Let's see what it looks like on the graph. Even if it's 1 minute, I put in 1 minute, it's $2. So you can tell over on the graph that 2 is 2, okay, 1 is 1, and you can see all of those little individual pieces. At 4, it jumps up there. At 6, all right. So you can see that it kind of creates what we call stairs or steps. Now the only thing is I got to talk about a function. Right now I'm confused as to how much I'm being charged for exactly 2 hours. Am I being charged $2 or am I being charged 4? And of course from the word problem we know that I'm being charged $2, so that at 4 I have to use an open circle. And that happens again and again and again on all of those. If you look back and follow the pattern, I think intuitively it feels like that's supposed to be open. And of course that does make sense that it's open, because if you rent it for no time, they can't charge you anything. Alright, this is called a step function because the function creates stairs. Alright, so we'll talk about the domain and range. Alright, the domain. Because the park's only open for 10 hours, I can only use the hours from 0 to 10. But if you notice, I use every single one of these hours. I use 1 hour, 2 hour, 3 hour, 4 hour. I also use half an hour, 1.5 hour. I use every single possibility between 0 and 10, except for 0. 0 doesn't count. 10 does count, but 0 does not count. Now for the Y's, what kind of Y's do I get? Well look, I'm charged $2, or I'm charged $4, or I'm charged 6 or 8 or 10. But am I ever charged anything besides that? Am I ever charged $3? No. Am I ever charged $2.25? No. So that's kind of looking through those. I'm going to let the rest just run through without much description, but you can watch it at your leisure. Alright, this one I hope you recognize was unique, because right here it said up to $25 for the day. So once I got right here, once I rented it for 5 hours or 6 hours or 7 hours, I was maxed out. I was never going to get more than $25 per day. Okay, the greatest integer function is a special little function that looks like this. It's also a step function. Okay, and it's got these funky looking brackets on it, and that's what we're going to use. Alright. It's defined as the greatest possible integer that is less than or equal to whatever number x you're looking at. So before we graph this, I'm actually going to look at the evaluating. What number is the greatest possible integer that is less than, or it could be equal to, the number 3. Of course, that answer is 3. Alright, well, that's because 3 is already an integer. Now, this one's a little trickier. Actually, it's easier. What number is the greatest possible integer that is less than or equal to 1.5? Well, there is no integer equal to 1.5, so I have to be less than that. Which one's less than that? 1. Have the idea of that now? What integer is the greatest number that is less than or equal to 0.99? Well, since 0.99 is not an integer, I have to go to the one less than that, which is 0. 5/3 would be 1 2/3, so the greatest integer is going to be 1. And negative 2.7, thinking about our negative signs, going the other way, it's negative 3. The graph looks like this, and it's just something for you guys to kind of be familiar with. We're not really going to do any work with it.